Hello everyone and welcome back to the Calculus Fun Room. In this video we're going to pick up where we left off from the last video where we were talking about parametric equations. Now in the last section we focused mainly on graphing parametric equations, conceptually what that looked like. And then in this section, we're going to take that conversation further. We're going to look at calculus of parametric curves. So a couple concepts in particular we're going to look at is slopes of tangents, areas, and then we'll look at arc length and surface area, a couple applications. Now if we think back, I'm going to draw a quick rough sketch. If we think back to the very last video, actually, let's come back to that. The very last example in that video, we talked about a projectile motion. So we talked about having a projectile being launched, and we had some equation for x as a function of time and for y as a function of time. Now when we think about the motion of this projectile as it moves along its path, right, that point xy gives me the position of the particle as a function of time. And if I look at dx dt, so dx dt tells me how quickly the x direction changes, right? dy dt tells me how quickly the y direction changes. And we kind of mentioned that when we were talking about that projectile motion problem. So how quickly is the y changing would be dy dt. Now what we really want to look at, let's say when we're graphing in the Cartesian plane xy, the general convention of what we've discussed all throughout Calc 1 and Calc 2 is we look for dy dx. So if I just kind of redraw my graph and I think about dy dx, right? dy dx gives me, the slope of the tangent on that graph, right? So we typically want dy dx here. Now we can in application look at dx dt as we just discussed, and we could look at dy dt as we just discussed. But in a general concept, if we're looking for slopes of tangents, we're looking at a delta y over delta x for any particular curve in the Cartesian plane. So how would we develop the process in which we want to do that? And it really comes from the chain rule. So if we think about the chain rule, way back in Calc 1, the chain rule, we had something along the lines of, if we had y as a function of x and x as a function of u, that was how we presented the chain rule. But instead of having the u variable, we have the t variable here. So the chain rule would say that dy dt is going to equal dy dx times dx dt. And the cool thing about the Leibniz notation, right, we can kind of see here that the dx differential, right, would cancel out. So without doing any real major derivation here, the derivation really comes from the chain rule and how I would develop the derivative dy dx. So what I'm looking for is the dy dx here, right? So I'm going to divide both sides of that equation by dx dt, and there is my formula, if you will, for finding dy dx. Now in the prior video, one of the things we had done when we were graphing parametric curves is we had eliminated the parameter. Now that isn't always an option, and in really most interesting situations we can't do that, or it's just extremely laborious and tedious. So what I don't want to have to do is do some substitution with my two parametric equations to eliminate the t. I don't want to have to get y as a function of x. So this formula allows me to not have to deal with that process. Now in a similar manner, it might be advantageous to find the second derivative of a parametric curve. And keep in mind, conversationally, that means we're going to take the derivative of the first derivative. Now what we don't have is dy in terms of x, right? We have dy dx in terms of dy dt and dx dt. So the way that we're going to do this procedurally is we're going to find the derivative of dy dx and then divide by dx dt. So here would be a formula for the second derivative through that process. I want to take a look at an example here to illustrate what these look like. And let's say we have the equation x equals t squared and y equals t cubed minus 3t. So let's do a couple problems here. Let's say part A. Let's show the curve has two tangents at the point 3, 0 and find their equations. So just want to explore visually what we're looking at, right? What we're being asked. So I'm bringing up my TI calculator and I hit the mode key and make sure I'm on parametric mode, so that when I hit the y equals key, I'm going to plug in our equation. We had x equals t squared and we had y equals t cubed minus 3t. Alright, so now if I graph, here's that equation. Now, I was in a weird window prior, so I'm going to change to zoom. Let's do zoom decimal, see what that looks like. And then also, we talked about when we look at graphing, we typically go 0 to 2 pi. Again, I was playing around with this in our prior video. So let's go minus 10 to 10, take a look at our graph, and we can see at the point 3, 0, we do have two tangents, right? So the graph is coming in, looping around, and going out in that direction. So to find the equation of those two tangent lines, right, we need the derivative in order to find the slope of those two tangents. So I have, from our chain rule, right, that dy dx is going to be dy dt divided by dx dt. And let's see, if I come back up to my y equation here, dy dt is going to be 3t squared minus 3, and then dx dt is going to be 2t. So our dy dx is in terms of the parameter t. And remember, we discussed that what we don't want to do is have to solve for y as a function of x. So in the parametric form, our derivative will always be in terms of t here. Now, if I want to find the equation of the tangent, what I need to do is find, in this case, the value of t that corresponds to the point 3, 0. Right? So I need to figure that out so I can plug into the t value of my derivative. So I'm going to come back up to my x equation that I highlighted in yellow up there, and I'm plugging in x equals 3. So again, I'm at the point 3, 0, and I'm going to plug in x equals 3. And so plus or minus root 3 are the t values that correspond to that point. Now, if we come back to our calculator real quick, I'm going to hit the trace key and I'm going to do second square. So let's look at root 3, and we can see that we correspond to that point. So the positive root 3 is when I'm moving in that direction, right? You know, think about this for a second. Let me go to negative 2. And I'm at that point, and as I let t increase, right, you see how I'm moving along the curve. So positive root 3 and negative root 3 are corresponding to that same point at 3, 0. So then let's see. So the slope at t equals negative root 3 is going to be 3 negative root 3 squared minus 3 all over 2 times negative root 3. So negative root 3 squared is 3, times 3 is 9, minus 3 is 6 over negative 2 root 3, and that's, what is that? Negative 3 over root 3, which I guess I could rationalize that if I multiply by root 3 over root 3. That's going to give me negative 3 root 3 over 3, which is just going to give me negative root 3. If I plug in t equals positive root 3, so we had our two t values corresponding to that point, so I'm going to plug in positive root 3 into my derivative, and you can see the only thing that's going to change really is the sign in the denominator. Oops, so it was negative root 3 in the first one, now it's just positive root 3. So all that's going to change is, instead of my slope being negative, my slope is now positive. So to find the equation of the two tangents, basically, I have y minus y1 equals m times x minus x1. And I have that for both slopes, right? So I'm going to plug in my point, and I'm going to do this twice. So my ordered pair was 3, 0. Right? My xy ordered pair that we had up here was 3, 0. So I got y minus 0 equals let's do the negative slope, right? X minus 3, right? So obviously y equals negative root 3x plus 3 root 3, and then we're going to get the same thing over here, right? Y minus 0 equals positive root 3 x minus 3, so we're going to get y equals root 3x minus 3 root 3. Now if I want to graph these in my calculator, remember I'm in parametric mode, I'm not in function mode. So to graph this on my calculator, what I'm actually going to do is I'm going to let x equals t, and then I'm going to let y equals negative root 3t plus 3 root 3, and that'll graph as a set of parametric equations that tangent line, and then I'll do the same thing over here. I'll just let x be the parameter and let y be root 3t minus 3 root 3, and I just noticed a typo there, and I wrote x, so that should be just a 3. So let's take out our graphing calculator and graph those two tangents to see what they look like visually. So on my TI-84, I've plugged in both sets of parametric equations for those tangent lines as we wrote on the digital board. And if I go ahead and hit graph, we can see those two tangents to that parametric curve passing through the point 3, 0. Let's take a look at part B. And part B asks to find the points. I'm going to get lazy with my grammar, right? Find the points where the tangent is horizontal and or vertical. So we're going to look for both. So bringing the graph back up just to take a look visually what we're talking about, we can see that there would be a couple points here where the graph has a horizontal tangent, and we see one where we would have a vertical tangent. Now on our notepad, I'm going to switch to red real quick, we can see horizontal tangent kind of in those upper and lower points of the graph. And then if I switch to blue, we can see a vertical tangent here, it looks like where it hits the y-axis. Now if we think back again in terms of dy dx, right, dy dx is giving me slopes of every tangent. So just like we would have done in prior conversations, the horizontal tangents come where dy dx is equal to 0. Now, if we think back, I'm going to scribble down here, if we think to our formula for the parametric version of our derivative dy dx, what we're really looking at in that case is where the numerator is equal to 0. The only time a fraction is equal to 0 is when its numerator is equal to 0. Now in this case, because we're looking at parametric curves, or we could be dealing with things that are not functions of x, so we could very feasibly have a vertical tangent as we see in this graph. And if I come back and look at my derivative, the only time I'm going to have a vertical is if my slope is undefined. So when will dy dx be undefined? That's where the denominator dx dt is equal to 0. So for this particular example, what did we have? I forget. X equals t squared, y is t cubed minus 3t. So we had x equals t squared and y equals t cubed minus 3t. So to find the horizontal, just because that was the order in which we went, we're going to set the numerator equal to 0. So I'm going to come over here and let's say horizontal tangent, and we're going to set dy dt equal to 0. So for this example, we have 3t squared minus 3. Here's our y equation. So 3t squared minus 3 equal to 0. We're going to get 3t squared equals 3. T squared equals 1, and t equals plus or minus 1. And again, that makes sense visually. If I come back up to my graph, there's two places, t is positive 1 and t is negative 1, where we're going to get horizontal tangents, and what we drew in red are the two horizontal tangents that we have up there. So if we think of the graph sketching in that particular direction. Oops. So t equals -1 must be this first point, and then t equals +1 is that second point as we continue in that direction. Now, I think what we should probably do is go ahead and find the ordered pairs there. So we know that x is t squared and y is t squared minus 3t. And I think we could just look at that graph and tell what the ordered pairs are. But if t equals -1, the point xy, so if t is -1, I'm going to get -1 squared, which is 1. And if I plug into that y equation, I'm going to get -1 cubed, which is -1, plus 3. So I'm going to get -1 plus 3, which is 2. And then if t is +1, my point xy is going to be 1 as my x. And let's see, 1 minus 3 is going to be -2. So 1, 2, and 1, -2, which again, we can see here's the point 1, 2, here's the point 1, -2. Now the second one would be to find the vertical tangent. And again, the vertical tangent is going to come where my slope is undefined. So we're looking at where my denominator dx dt is 0. So for this example, dx dt would be 2t, right? Again, looking at yellow up there, x is t squared, so dx dt is 2t, and that's just going to give me t equals 0. So again, if I come back up to my graph, t equals 0 is corresponding to that point at the origin. So what's the ordered pair? So the point xy is going to be, so if t is 0, x is 0, and y is 0, right? Which was at that origin. So let's look at a part C where we would consider the second derivative, because we had talked about the second derivative formula. So let's look at that in this particular example. So let's suppose we want to find where the curve is concave up or down. We're going to look for both intervals. And again, remember from a Calc 1 conversation, right, concavity comes from the second derivative. So what we're looking for is d squared y dx squared. So the formula that we wrote up at the beginning of this video is we're going to take the derivative with respect to t of dy dx, and we're going to divide by dx dt. Now, we're taking the derivative with respect to t of dy dx, and we have dy dx. Where's dy dx at? Dy dx was, well, we didn't officially build dy dx, right? So dy dx that we have here is going to be dy dt over dx dt, right? So for x equals t squared, y equals t cubed minus 3t. Let me rewrite. I want to have that reference here. Okay. So we have x equals t squared, y equals t cubed minus 3t. So when we plug in to our second derivative formula, right, our dy dx was dy dt over dx dt. So the reason, just to point out to you here, the reason our formula has us finding dy dt of dy dx is that's because dy dx is in terms of t. So when we're doing our second derivative, we have to be finding the derivative with respect to t of dy dx because it is in terms of t. So in the numerator, excuse me, we're going to have a quotient rule there. So I'm going to have bottom times derivative of the top minus top times derivative of the bottom all over the bottom squared, and I'm going to divide all of that by dx dt, which was 2t. So I just pause the video for a moment to go ahead and do the algebra of that expression. So when I simplify all of that, I end up with 3 times quantity t squared plus 1 all over 4t cubed. Now remember, for concave up, what we're looking for is where the second derivative is positive, right? Now if I look at this expression in my derivative, notice the numerator is always positive, right? Any t I plug in, I square it and then add 1, right? So that's always positive. So really the only thing I'm considering here is the denominator. So where's 4t cubed going to be greater than 0? So that's only really when t is greater than 0. Now if we think back to our graph that we sketched up here, right? When t is positive, right? So when t equaled 0, let me change to red. When t equals 0, we are here at the origin, and then as t goes through positive values, we're looking where my graph is concave up. So that makes sense visually there. And then if I come back and just kind of repeat that same conversation, right? Concave down is going to be where the second derivative is negative. And so in that case, right, we're really looking at where only the denominator is negative, and then again, that's just going to be where t is negative. So visually speaking, right, remember as t is negative, we're moving in this direction. So all the way up to t equals 0, we can see visually the graph would be concave down. And then from t equals 0 out to positive infinity, we can see the graph is concave up. Let's take a look at another example, and let's look at one that involves some trig functions, just because these usually cause some issues. So let's consider the curve x equals cosine theta, y equals cosine of 3 theta. And let's just ask the question, find horizontal and vertical tangents. All right, where are those? So again, if we think back to our derivative, right, our dy dx equals dy dt over dx dt. And let me stop a second and discuss the variable theta here. Remember, theta is really playing the role of a parameter in this situation. I'm still plotting ordered pairs x comma y, and theta is just describing the location of that point xy. So what particular angle theta produces the point xy on my curve. So even though we're not using the letter t, we're treating theta as our parameter. So I want to visualize what this graph looks like for a moment. So here's x equals cosine t, y equals cosine 3t. And again, when I'm in parametric mode, I'm not using the letter theta, I'm using the letter t. So if I hit graph here, I see this graph, and what I notice is the graph looks really thick, right? Check this out. If we think about theta for, let's say, the cosine function, the period is 0 to 2 pi, and if I look at my window, I'm going way outside that period. So I have to be getting some repetition here since I'm going outside the interval 0 to 2 pi. And in fact, if I go back to the graph and I trace and I start to hit my right arrow, you can see we are most definitely tracing this curve multiple times. So I just want to go to the window. Let's change my x-min to be 0, my x-max to be 2 pi. Excuse me. And then let's graph again. So if I trace starting at 0 and I let t increase, I go once and then I come back twice a second time. So actually 0 to 2 pi is giving me the graph twice. So I think I really only want to consider this curve from 0 to pi so that we're only finding the horizontal and vertical tangents within one cycle or one period of this graph. Now what's also unique when I look at this graph, notice I don't really have any vertical tangents. It looks like I only have horizontal, but suppose we don't have the graph at the moment, and we're going to come back and we're going to figure that out, right? And visually we'll connect to what we see here. So coming back to our digital notepad, right, our horizontal tangents are going to come from the numerator being equal to 0. So we're looking for dy d theta equal to 0. So in this case, dy d theta is going to be, what do we got here? So derivative of the outside, derivative of cosine is negative sine 3 theta, and then times the derivative of the inside. So let me just pull out that constant out front. And then we're going to set that equal to 0. So that's where sine of 3 theta, is equal to 0. So the only time sine is equal to 0 is if I have sine of 0, sine of pi, sine of 2 pi, sine of 3 pi. So my angle inside has to be 0 or pi or 2 pi or 3 pi dot dot dot. Now, when I graph, or I divide both sides by 3, right, I'm going to get 0, I'm going to get pi over 3, I'm going to get 2 pi over 3, pi, so on and so forth. Now remember, when we graphed this equation, right, we were graphing for theta between 0 to pi to just give us that one period there. So coming back to my graph, if I trace to theta equals 0, notice we're picking up sort of a extraneous solution here. Theta equals 0 does not correspond to a point where my tangent is horizontal. So we'll discuss why in a moment. So then my next one was pi over 3. So if I plot that point, there is the first horizontal tangent, and if I trace to 2 pi over 3, we will see the other horizontal tangent. There's that guy, and then obviously if we trace to pi, we're going to see that other point. Oops, if I do to pi, we're going to see that other point at the end. Now if we're looking for the vertical tangents, right, we're looking for where we would have division by 0. So we're looking for this case, dx d theta being 0. Right, so x is cosine theta, right, if we're looking back up at our equations here. X is cosine theta, so dx d theta is negative sine theta, and when is that equal to 0? So, negative sine theta is going to equal 0. Again, sine of 0, sine of pi, sine of 2 pi, so on and so forth. So the thing inside the sine function has to be 0, pi, 2 pi, so on and so forth. Now, if we think of our domain as being just 0 to pi, before we start to retrace our graph, we can see theta equals 0 and theta equals pi are the two that satisfy that. And then, let me come back to our other solution. We had 0, pi over 3, 2 pi over 3, and pi. Now remember, on this other graph, right, or excuse me, I should say for the horizontal, the pi over 3 and the 2 pi over 3 were really our only two solutions for horizontal. And if we look at the 0 and pi, that's where I'm going to have division by 0. So that's why the 0 and the pi aren't being included in those horizontals, because I have division by 0 at those points. So my tangent is undefined. Now why don't I see the vertical tangent there? Well, if you think about this for a moment, I'm getting division by 0 at 0 and pi, but my graph stops and changes direction in that case. So there's not really a vertical tangent, and because the derivative is undefined, that also identifies, corners of my graph or an endpoint in this case. So I definitely have an undefined derivative at that endpoint, but there is no vertical tangent. Let's take a look at another example where we are utilizing the derivative, and then we'll move on and take a look at some other concepts like area and arc length. So in this example, let's say we want to find the rightmost point on the curve defined parametrically as x equals t minus t to the 6th and y equals e to the t. Now, I want to visualize this so we can just kind of see conceptually what it is we're looking at. So bringing up my TI calculator and plotting this parametric curve, we see this basic shape. So we can see that we have a rightmost point here. And if we think, kind of conceptually, physically about what's happening there, right, obviously the rightmost point, we're going to have a vertical tangent. So we're looking where the derivative is undefined in this case to find that vertical tangent. So once again, if we think back to our derivative of our parametric equation, dy dt over dx dt. Right? So for the horizontal tangent, for this case, we want a vertical tangent to find that rightmost point, right? And that's going to be where we have division by 0, so we're going to have dx dt equal to 0. So for this particular set of parametric equations, if I'm looking back up at my x equation, right, dx dt is going to be 1 1 minus 6t to the 5th, setting that equal to 0, we are going to get, what is that going to be? 1/6 equals, sorry, my brain's working slow, and then I'm going to 5th root both sides. So I'm going to take the 5th root of 1/6, and that should be my t value. Now if we bring our graph back up on our calculator, I'm going to hit trace, and I'm going to divide by, let's see, 1. I'm going to trace to 1 divided by the 5th root of 1/6. So I'm just going to do 1 over 6th raised to the 1/5 power, and instead of typing 5th root. And let me hit enter, and we'll trace to that rightmost point. Let's take a look at the next concept where we're going to discuss area. Now remember, we're still graphing in the Cartesian plane. We're still looking at y as a function of x, but we're describing that curve parametrically. So if I think about area under a curve, right, we might typically look at something like this in a generic form, and so we're looking for that area under the curve. So what we would talk about back in a Calc 1 course is the area under a curve. Like, let's say we were going from A to B. So the area would be the integral of f of x dx, if you will. And to connect to how we're going to deal with this with parametric curves, I'm just going to write that as y dx, where we know y is f of x in that case. Excuse me. Now what we're going to do here is basically substitute, right? Because we don't have y as a function of x. We don't have that equation. But we do have y in terms of the variable t. So if I'm thinking of this equation, and I apologize for the same letter here. So x equals f of t, y equals g of t, right? That's typically how we would describe parametrics. So just to avoid a little confusion, let me call this capital F, right? So we have y equals cap f of x, and we would be integrating cap f of x. So x equals lowercase f of t, y equals lowercase g of t. So I am just going to plug in the y, and I'm going to plug in the dx, right? So the dx would be, oh man, I have a typo there as well. My y is g of t. Here's my y, that's g of t. So I have g of t, and then the dx is going to be the derivative of the x equation. So if I look at the x equation, I'm taking its derivative, which is f prime of t dt. So almost like a u sub, and I have to replace that dx term. Now we have a variable of t for our integral, right? That is our independent variable in that integral. So we need t limits of integration. So the a to b that corresponds to those 2 points, I'm going to have values of my parameter that get me to those locations. So typically in the calculus textbook, we're going to call that alpha and beta, right? Where t equals alpha corresponds to x equals a, and t equals beta corresponds to x equals b. Let's look at an example to illustrate this concept. So suppose in this example we want to find the area between the curve my fingers never want to work, between the curve and the x-axis. So the curve is going to be defined parametrically. So to visualize this idea, right, of this problem, here's plugging in the parametric equations for this curve. Let's go ahead and graph, and we can see, let me go ahead and fix that window. Let me do zoom standard. And of course, when I fix the window through a zoom, it changes to 0 to 2 pi. So let me change my x-min, x max minus 10 to 10. So, we're looking, the way this problem is posed, for the area between the curve and the x-axis, right? So that's meaning that we're enclosing that particular area. So we need to find that x value for that first x-intercept, and we need to find that x value for that second intercept, and then we're going to integrate under our function. Area, again, being the integral of y dx, and we're going to plug into each of those. We're going to substitute, right? So my y is the 2t minus t squared, and then the dx, derivative of the x equation, is 3t squared dt. Now remember, we're looking at those x-intercepts, right? Excuse me. So to just visualize what we're looking for there, we want those x-intercepts. So typically, or I should say not typically, always, when I'm finding x-intercepts, I'm setting y equal to 0. So I'm going to take my y parametric equation and I'm going to set y equal to 0 to find the t values where I hit the x-axis. So I'm going to factor out a t. So we can see at t equals 0 and t equals 2, those are going to be the first and second times in which I hit the x-axis. So those are going to be my limits of integration on my integral. So now let's go ahead and work this integral out. If I FOIL, or technically distribute, and take my 3t squared, distribute in, I'm going to get 6t cubed minus 3t to the fourth dt, and taking the antiderivative, see, add 1 to the power, divide by the power, add 1 to the power, divide by the power, and we're going to go from 0 to 2. I paused the video real quick just to save a little bit of time through that arithmetic. So plugging in the upper limit of 2, then subtracting with the lower limit of 0 and crunching that result, I get 24/5 as the area under the curve. And the next concept I want to take a look at is arc length. So let's suppose we want to consider the length of a curve described parametrically. Now, just to remind you from prior video where we discussed arc length, for a function y equals f of x from a to b, I'll do a rough sketch here from a to b, right? We were looking for the length of that curve. So when we developed, right, we derived that formula, and we ended up with the integral of 1 plus dy dx squared. Now, to remind you where that idea came from, what we did was we broke this curve into line segments. Right? So we broke it into inline segments. The inline segments gave us an approximation to the length of the curve, and then we took a limit as n went to infinity. Right? That was the limit of the Riemann sum, which produced this integral. Now, what we're going to do in this case, so basically what we're looking at here is the distance formula. Right? When we did that derivation, that was what we discussed, right, as we took that limit. Now, the issue here is we don't have the Cartesian equation. We have parametric equations. Oh, man, and I keep using the same lowercase f just to avoid confusion. So we have a formula for dy dx. So for our formula for dy dx, we have, and I'm not going to give myself enough room here, we have dy dt divided by dx dt. So we have the square. There's our dy dx. Now what we want to be able to do, oops, I left the differential off up on that top piece. So what I need to be able to do in this case is a couple things. I need to connect to the fact that this derivative is going to be in terms of the parameter t, but I have an issue where my differential is in terms of the variable x. So I need to convert that differential. And there's a couple different ways that we can do this. What I like to do typically when I present this concept in my face-to-face courses is I do a little bit of algebra with this expression under the radical to see how we can introduce that dt expression. So let me just kind of come over here, and I'm going to call this, a little bit of side work that I want to do to just show ourselves, right, kind of derive where our formula comes from that we're going to end up with in just a moment. So what I'm going to do in this case, I got to give myself a little more room. I am going to, in fact, let me skip this first line. Well, you know what, let me write the first line. So I would have dy over dt squared and dx over dt squared, all under the radical, times dx. I'm just going to leave the integral symbol off for the moment, just to do some manipulation with that radical. Now, what I'm going to do is factor out the dx dt squared here. So, and in fact, let me leave that for a moment. So I'm going to factor out 1 over the dx dt squared, right? So I'm basically factoring out the dx dt out of the denominator of that derivative process. So when I do that, what that gives me is a dx dt from my 1, and then a dy dt from the derivative. And if you think about this for a moment, right, if I take this expression and I distribute it back in, when I distribute it in here, it goes back into the denominator, and when I distribute it in here, I get dx dt squared divided by dx dt squared, and that's just 1. So that was some legitimate algebra that we dealt with there. And then I'm going to basically take out of the radical that term that I factored out. All right, so I need to go ahead and not extend that radical that far. So when I pull that term out of the radical, right, I basically have the radical of 1 over a squared, if you will, and that's just going to come out as 1 over a, right? So the radical undoes the square that we have there. And then I'm going to flip and multiply, because I have a compound fraction here. So I'm going to flip and multiply this as dt over dx times the dx that we have there. And we have that radical. I'm just going to get lazy. We know what goes under that radical. And then we can see the dx's cancel here, and I end up with just a dt. So this whole expression converted to dx dt squared plus dy dt squared under the radical, and then I have that dt differential that I needed out front. So where did I scribble, right? So in the very beginning of our work, up here at the very top, we had the dx. That was a problem because the derivative inside is in terms of t. So now we have our expression, our integrand, with the dt differential. So in terms of parametric curves, the arc length is going to be the square root of, we're going to take the derivative of the x term, square it, derivative of the y term, square it, and then dt. Now again, the way we typically write something like this in a calculus textbook is t is going from alpha to beta when we're thinking of, our curve going from a to b. So t equals alpha corresponds to that first point, t equals beta corresponds to that second point. So we have a curve, again, in the xy plane, or in the Cartesian plane. We're describing that curve parametrically. This would be our arc length formula for how to calculate the length of that parametric curve. Now, when you look at this formula, it kind of intuitively makes sense, right? If we think about the distance formula is, the square root of the change in x's squared plus the change in y squared. So usually in an algebra course, we have the square root of delta x squared plus delta y squared. So we can kind of see that connection to the distance formula that we already know. Let's take a look at a quick example on how we would apply our arc length formula. So let's say we want to find the exact length of the curve x equals t sine t, y equals t cosine t from 0 to 1. Taking a look at this visually, plugging in my parametric curves, parametric equations, and I want to only look 0 to 1 on this graph. So let's graph and we can see there's our length from 0 to 1. We're going to find that measurement for this set of parametric curves. Using our arc length equation, right, we have the integral of square root of dx dt squared plus dy dt squared dt, and we're going to be going from 0 to 1 in this case. I'm going to come over here to the side, or I'll do it down here below. Let's just do a little bit of the derivative work outside the integral. So if I'm looking at my x equation again, here's my x and my y equation. So dx dt, I'm going to do a product rule. Let's say derivative of the first times the second plus first times derivative of the second. And I'm going to have to square that result. So let's go ahead and square that result. I'm squaring a binomial, so I'm going to square the first, multiply the 2 and double, and then square the last. Now for just a moment it looks like I might be able to clean this up, but I can't, right? It looks like I have sine squared plus cosine squared, which equals 1, but that t squared coefficient on the cosine messes up my ability to do that. So we won't try to clean that up yet. And then let's see our dy dt. So the y equation up there in yellow, dy dt is going to be the same type of thing, product row, right? So derivative of the first times the second plus first times the derivative of the second. And really, so what do I got there? Cosine t minus t sine t, right? And then if I square that result, I'm squaring a binomial, so that's going to be square the first, multiply the 2 and double. Oh, looks like I'm going to get some nice stuff canceling out here, and then square the last. So let's just continue with the algebra. I'm going to get lazy and step away from the Leibniz notation for a moment. So let's see, if I add these two together, let's take a look at what we're going to have without me having to rewrite all of this stuff. So I'm adding the x prime squared and the y prime squared. So I'm going to get a sine squared plus a cosine squared, which is going to be 1. I am going to have 2t sine t cosine t minus 2t sine t cosine t. And then I'm going to get t squared cosine squared plus t squared sine squared. Now the cool thing about that is the t squared is going to factor out, right? And I'm going to get, well, I wrote it in the wrong order. I'm going to get sine squared plus cosine squared there. I have my 1. So all of this becomes 1 plus t squared. So I have the length being the square root of 1 plus t squared dt as t goes from 0 to 1. When we look at that integral, square root of 1 plus t squared, we could do trig substitution with that. So in a prior chapter where we learned the techniques of integration, we would have done trig sub, where we would have put that radical on the hypotenuse, and then we would have had t and 1, and we would have done the substitution that t is equal to tangent of theta and worked through that integral. Now that's a very long integral to work out. That is not the concept of this particular chapter, so I'm going to go ahead and skip that work. That'd take us about 10 minutes to do that. So here is our integral. Now usually in this type of chapter you would be allowed to look up integrals in a integral table. So if I looked in an integral table, I would find that result. And now we're going to evaluate from 0 to 1. Plugging in upper limit minus lower limit, we get 1/2 root 2 plus 1/2 ln of 1 plus root 2. So again, the concept here is finding the arc length of a curve, and just to scroll back up, we went through the derivation of converting our arc length formula the square root of 1 plus dy dx squared dx and putting that into the parametric form we have here in red. And then this example is just to illustrate how that formula would work for us. Now, a lot of times within a homework set of problems, when you get to this final integral for a specific example, sometimes that integral may be a little nastier than others. So, obviously, talking to your calculus professor to see what the expectation is there, but typically you would use an integral table to get to that result. Taking a look at the last concept in this section, in this video, would be surface area of parametric equations. And I just want to remind us real quick, in a prior video, which would be section 8.2 out of Stewart's textbook, we talked about surface area of revolution. And the way we kind of visualize this is we had some function, let me use capital F this time, right? Say we would take that curve and rotate around the x-axis, if you will, and we would envision rotating that curve something like this, and we'd have something like that on the bottom once we rotate. All right, that was sloppy. So we'd be looking at the area of that surface. So we ended up developing a formula where we talked about if we rotated around the x-axis, we would have 2 pi y ds. And we denoted that the ds would be the length of the curve. We called that the piece of length, right, our arc length expression. And so for the parametric curves, right, just like we talked about, that piece of length is going to be dy dt squared plus dx dt squared. Now, obviously, if we're looking at a parametrically defined function, the way that we typically write this, then what we're doing is just like we did with the area conversation, we're just going to replace the y. So we're just going to replace our y and our expression here and our integral with the y equation that we have defined parametrically. Right? So we could write that as 2 pi, and then the y would be g of t, and then our square root of dx dt squared plus dy dt squared. And we also talked about if we took a curve and we rotated around the y-axis. So this was about the x-axis. Sorry for my bad organization here. Right, this was about the x-axis. That if we rotated about the y-axis, what we would use as our formula, and again, I don't want to derive all of this. We already derived this in a prior video. We would utilize the formula 2 pi x ds. So again, very similarly, we're going to represent the x in our equation. Right? We're going to replace it with our parametrically defined x equation with the ds, which we have written as square root of dx dt squared plus dy dt squared. So we would have 2 pi f of t, and then our ds. Alright, so this video is getting pretty lengthy. I don't want these videos to be too long. I think at this point you understand how I would plug into that formula without spending 10 minutes to work through a specific example here. So this really finishes the conversation on parametric curves in the Cartesian plane. So in our first video, 10.1 out of Stewart's book, we just kind of looked at an introduction to the concept of graphing Cartesian equations to create, parametric equations to create a Cartesian curve in the xy plane. And then in this video, we have discussed kind of calculus of parametric curves. We talked about tangents, talked about area, surface area. So this really kind of finishes and wraps up that conversation. And in the next couple videos, we're going to take a look at graphing with polar equations and the calculus involved with that. I look forward to seeing you in the next video.